Let's now take this idea of instantaneous rate of change and see if we can apply it to a problem here. So here I have a rock that is launched vertically upward from the ground with an initial speed of 96 feet per second. The position of the rock in feet above the ground after t seconds is given by the function s of t equals negative 16t squared plus 96t. Consider the point P, which is 1, 80 on our curve S of t. So we're going to consider both of those things. Part A says find the instantaneous velocity of the rock 1 second after launch and find the slope of the tangent line to the graph of S at P. So it sounds like the question is really asking me for two different things, but instantaneous velocity is really just another way to talk about instantaneous rate of change. Here our change is just in the change in position, the change in position. So if I want to talk about the change in position, right, if I want to say the rate of change, so in other words, how quickly did I move from one point to another point, you might say, oh, well, the way we would talk about that is using speed or velocity here in this case. So if I want to talk about the rate of change of position, we're always talking about velocity. And this is a really, really important idea really for the rest of this class, is this idea of position and velocity being very much related, that the instantaneous rate of change of position is velocity. And if we know the instantaneous rate of change, well, we said also that that's another way to talk about slope of the tangent line. So slope of the tangent line, here actually let me write these down. If I want to talk about instantaneous rate of change, this tells me the same thing as the instantaneous velocity, which tells me the same thing as slope of the tangent line. So this seems like a fairly important, tangent line. This seems like a fairly important quantity here. That quantity, again, remember, was the average rate of change between A and A plus H, so f of A plus H minus f of A. Take that divided by H, and then look at the limit as H approaches 0. What happens if we take the distance between those 2 points and we make them smaller and smaller and smaller? So if I want to find the instantaneous rate of change, and I do, let's see, I'm going to break it down into the same 4 steps that I looked at last time. So I'm going to start by looking at, rather than f, here my function is named s, so I'm going to say s of, let's see, what's my a here? My a here in this case is 1. That's the x value that we're talking about. I can also tell, because we want to know the instantaneous velocity after 1 second, and we also want to know the slope of the tangent line to the graph of S at P, which P again has an x value of 1 second. So I'm going to find S of 1 plus H first of all. And to do that, I'm taking 1 plus H and I'm plugging that into my position function up here, negative 16t squared plus 96t. So I should have negative 16 times 1 plus H quantity squared plus 96 times 1 plus H. So here we'll have to do a little bit of work. Again, this piece right here we will have to FOIL out. Be very careful. It's really easy to make a mistake that way. Negative 16 times 1 plus H times 1 plus H. Here, if you want to distribute the 96, we can absolutely go ahead and do that. This would be plus 96 plus 96H. My suggestion here would be to FOIL these two terms out first before you do anything with that negative 16. A really easy mistake to make is to distribute the negative 16 here and then also distribute it over here. You really only want to do one or the other. So I kind of dodge that question altogether, and I say, you know what, let's look at this part first, and then we'll come back and worry about the negative 16. So I'm going to say negative 16. If I FOIL that out, I'll have 1 plus 2h plus h squared plus 96 plus 96h. And what do I have then? I've got negative 16 minus 32h minus 16h squared plus 96 plus 96h. We'll combine our like terms. So what do we have here? We've got negative 16 and positive 96. Let's combine those two. That would give me 80. We've got negative 32h and we've got 96h, so that would be 64. So plus 64h minus 16h squared. It looks like that's about as simplified as we're going to get. So we've got that first part here, and oh my goodness, I didn't give myself enough room to write this out. That's okay, we can move into the next section a little bit if we need to. 2, I'm going to subtract this f of a right here. So I'm going to look at s of 1 plus h minus s of 1. So I'm going to take what I had right here. So that would be 80 plus 64h minus 16h squared minus, I want to subtract now, let me highlight, I want to subtract s of 1. Which you might say, okay, well, why didn't we do that in the first place? That's what you did in the last problem. And you could go and take 1 and plug it into your position function if you wanted to. But s of 1, I know the y value. That's just the y value of my function at x equals 1. So I know that in this case, another way for this to be phrased is to say s of 1 is equal to 80, because I know that that's a point on the curve. So I'm just going to subtract 80 here. And look at that, 80 minus 80, those two cancel. Let's see, I guess I'm going to have to double back up to the top here. So let me erase, let's erase this stuff right here. So I'm left with, at this point, 64h minus 16h squared. Step 3, let's do that in blue so that we don't get too confused here. I want to take s of 1 plus h minus s of 1, take this divided by h. So I'm going to take what I just found, which is 64h minus 16h squared, divide that by h, and remember, our goal is to simplify this as much as possible. Again, just like last time, I see that common factor of h in the numerator, so let's factor that out. I've got 64 minus 16h, all divided by h. These two cancel, leaving me with 64 minus 16h. My last step then, step 4, I want to look at, well, what's the limit as h approaches 0 of the whole thing? S of 1 plus h minus s of 1, all of this divided by h. So really I'm looking at what's the limit as h approaches 0 of 64 minus 16h. So here in this case, I'm just going to plug 0 in for h, just like I did last time. 64 minus 16 times 0 would give me just 64. So this is my solution to both of the questions they were asking me. So to let's erase this just to give ourselves a little bit of room here to summarize the result that we just ended up with. They asked, first of all, and let me erase just a little bit more here. Don't want to get too overwhelmed. They asked, first of all, find the instantaneous of the velocity the instantaneous velocity of the rock 1 second after launch. Well, the instantaneous velocity is equal to 64, but if we're talking about velocity, we want a unit as well. So we will want to check our units here. Our units for position are in feet. Our units for time are in seconds, so our unit for velocity would be feet per second. So the instantaneous velocity would be 64 feet per second. The other thing that this problem asked me to find was the slope of the tangent line to the graph of s at p. Well, we did that as well. Those two things are actually the same thing. So if I want to know the slope of the tangent line to our function s at p, which was 1, 80, this is equal to just 64. And remember that this is a slope. So here are both of our answers. It really says the same thing. We're just kind of interpreting them in two slightly different ways. We have the instantaneous velocity of 64 feet per second, and the slope of the tangent line is simply 64. So I'm going to use this idea here in the next part, part B. We'll find the equation of the tangent line in part A. So we want to find the equation of the tangent line, just in case we weren't specific enough here, at 1, 80 here. And this is just like the last problem that we did in the last video. We'll say, okay, I need a point, which I have that, and we need the slope of the tangent line. Well, oh my goodness, slope of the tangent line, we already found that. That's 64. So m is equal to 64. At this point, I have everything I need. So let's write the equation of our tangent line. Y minus y1, our y coordinate is 80, equals m, that's 64 as our slope, times x minus x1. Let's see, x minus my x coordinate, just 1 here. So y minus 80 equals 64x minus 64. Let's go ahead and add 80 to each side. So y equals 64x plus, what would I have there? Plus 16 should be my y-intercept. So there is the equation of my tangent line. It turns out I did all of the hard work in part A. This part I just needed to write the equation of a line really quickly. So the thing I really want you to take away from this video is to recognize that velocity is the instantaneous rate of change of some function, in this case of position. And remember that that can also tell us slope of the tangent line. These three things are very interconnected, and they will be for the rest of this course. So when I say velocity, I want you to start thinking about instantaneous rate of change. If I say slope of the tangent line, we should be thinking about rate of change. If I say velocity, we should be thinking, like, all of these three things are very much intertwined and really kind of talk about the same thing. They're just different interpretations of that same thing. So that same thing, that thing that we keep coming back to and talking about, seems like it should be really important if it means all three of these things, and that's actually what we're going to talk about in the next videos. We're actually going to define, well, what is this thing that is so important that means all of this different stuff? Well, that's going to be the derivative.